Okay, welcome back to NE 630, nuclear reactor theory. So last time we just discussed some principles from the modern physics or nuclear physics. Today we'll continue the first chapter of the reactor physics, the Stacy book. So let's start. Last time when I talked to you about the the abiding energy and about the fission, and there is a threshold for fission reaction. So I have to remind you is a concept for or a mechanism for the nuclear reactions, and this one of the nuclear reaction mechanism is called compound nucleus formation. So I will just give you a hint about compound nucleus formation, and later on in the I think in the next chapter we will be talking about the compound nuclear formation. How many of you heard about the compound nucleus formation before in any 495? Okay, so talk about compound nucleus formation. So if you have a neutron coming to hit a target nucleus, so this is the target, and this is the projectile, in this case neutron, then what happens is there will be a transition state or a transition reaction where the neutron will get inside the nucleus and it will form what we call compound nucleus. So this is called compound nucleus. And what happens is, if you look at the energy levels of the let's say this is XZA, and this is the neutron, which is 0, 1, does not have a charge but has a mass. So this will be XZA plus 1. So if we plot the energy diagram, we will notice that the nucleus XZA, this will be the ground state, and this is an excited level here. So if we look at the nucleus, the compound nucleus formed from the reaction, we'll notice that this is XZA plus 1, and then it will be excited at certain energy level. So the energy level here that the compound nucleus will be excited at came from two components. Let's say that this is the ground state, first excited, second excited, third excited, fourth excited, and so on. You can represent the nucleus like the atomic shells. There is something called nuclear shell model. So the nucleus can be represented by several models. One of the successful models is the nuclear shell model. There is another model that is successful in describing the nucleus. It's called liquid drop model. So both of them will describe the nucleus in certain aspects and fail to describe the nucleus in another aspect, and both of them work very well for the nucleus. So you can represent the nucleus like the atomic shells, but you have a nuclear shell. The only difference between the atomic shell and the nuclear shell, atomic shell, it's easier to bump one of the electrons from the ground state successively to the first, then you give it another energy to the second and third and so on until you release it from the atom, and in this case it will be ionized. So it is easier this way. In the nucleus, it is easier to raise a group of particles from one level to the second rather than moving one particle from the ground level to the upper levels. So this is one of the difference between the nucleus shell and the atomic shells. So in this case, this is the ground level for the target nucleus, and this is the ground level for the compound nucleus. The energy here, we'll call it EC. So this is let's say the compound nucleus energy, and the energy that will be given to this compound nucleus will be two things. E kinetic plus E binding energy. So the particle, or the neutron in this case, once it gets into the nucleus, will give the nucleus two components. The first one is the binding energy of the neutron inside the nucleus. Why? Because the neutron was free particle outside the nucleus. Once it gets into the nucleus will say, hey, come on, I will try to fuse you with your friends inside me. So once it fuses the neutron inside the nucleus, this energy will be liberated to the outside. And this is the binding energy of the neutron. And usually we call it the last neutron binding energy to the nucleus. This energy will be consumed to raise the excitation levels of the nucleus. So it will raise it to a certain level. And if the neutron also possess a kinetic energy, it will give this kinetic energy also to the nucleus. So the nucleus will have two components, the kinetic energy plus the binding energy. If both kinetic energy and binding energy giving to the nucleus is enough, when it is distributed over the particles inside the nucleus, if it is enough to liberate one of those particles, the compound nucleus will end up giving particle. So you will form the compound nucleus, then you will have a nuclear reaction. What's the nuclear reaction? It will be, if it is enough to give up one of the neutrons, it will be N reaction. And this is why we write it N XZA XZA and then N. So this is, it's called elastic scattering. Elastic neutron scattering. We will study this in detail. This is neutron elastic scattering. You get in, you get out, you do not lose energy. If let's say you get in with N, but you get out with N prime, what does it mean you get out with N prime? You get out with different energy. So this means that you will leave the nucleus, the nucleus that you left, you will leave it in a excited level. Then usually this is called inelastic scattering. Again, I will not write anything because we will go in details. So for the inelastic scattering, usually it will be followed by gamma emission. So if the energy is not enough to get any of the particles from the nucleus, so in this case you will produce an excited level or excited nucleus that will emit later on by gamma radiation. And this is called radiative capture. So you capture the nucleus inside, then you say, hey, I'm excited, I have enough energy inside. Then after 10 to the power of minus 14 seconds or so, you say, here it is, photon. So you'll emit the photon. And so you might emit the photon directly to the ground state, or you might emit the photon to another excited state, and you will still stay there for millisecond. Usually, if you are excited and you emit it to the ground, maybe it takes something like 10 to the power of minus 14, 10 to the power of minus 18 seconds. This is called prompt gamma emission. So if it's not prompt and you emit it to a certain level like this, usually the nucleus is still ZA plus 1, but with asterisk. And we call this isomerism. So it's isomerism state. So we call the nucleus is in isomerism state. It has excitation energy, but the level of this excitation energy is long enough, so this nucleus will stay for a little bit more longer than normal excited. You can emit again, you can emit alpha particles if the excitation energy, after you divide it by the particles inside the nucleus, is so huge, you can distribute the energy over 2 protons and 2 neutrons, and you will emit alpha particles and so on. So just I want you to understand the concept of the compound nucleus formation. Did you understand it? Did you have any question so far? So usually, if we are talking about any of the nuclear reactions, for example, we will note that there is nuclear reactions. We can classify them to 3 types. Again, we will study this later on. The first thing is something like hard sphere collision. So you have a particle, projectile, and then you have a target, and they will meet each other, hit each other as if they are billiard ball. So this is hard sphere model. They did not get inside each other. So this is just a billiard ball collision. And this is usually the elastic scattering reactions going on the nuclear reactors. So when the neutron will get out of the fuel, it will encounter the water, and the water is just H2O. So because the hydrogen has comparable mass like the neutron, they will play with each other like billiard ball. And from mechanics, you will know that the most favorite energy losing situation is when you have two equal masses. If you have a marble and you have a soccer ball, and the marble hit the soccer ball, it will bounce back without losing any energy. So, but if you have two marbles, maybe you will hit one of those marble, the projectile will stay still, and it will give all the momentum to the target, and the target will take all the energy and leave. So this is the most favorable condition. And this is why we have in the nuclear reactor, we have H2O. Why? Because hydrogen is similar mass like neutron, and this is how we reduce the energy of the neutron. At only one collision, maybe we will lose all the energy from the neutrons. So this is one of the concepts of nuclear reaction. The other one is what we call the compound nucleus formation, and the neutron will get inside the nucleus, and then you have the energy gain for the nucleus, and then the nucleus will be excited. The energy will be distributed among the nucleons inside the nucleus. Whatever energy is enough, if the energy is enough and beyond the threshold for the reaction will take place. The third one is called shape or mix between both, between the compound nucleus and shape, and it has quantum mechanical manipulation that we will not go through right now. But at least we will study the Breit-Wigner formula for the resonance in a chapter or two, and you will be able to understand this one. So let's just give a little bit of review of what we mean by neutron cross-section. What we mean by neutron cross-section. So as long as you are a nuclear engineer, you will live, you will die, you will have all your life with cross-sections. So everybody will ask you about, oh, what's the cross-section? What's this value, and so on. So you have to understand the concept of cross-section. Let's assume that we have a beam of neutrons. And when we say beam, we mean they have one velocity, so they are monoenergetic, and they have one direction. So this is why we mean beam. So let's say we have imaginary cylinder around the beam. So this is the cross-section for the beam, let's say. And we have imaginary cylinder like this around the beam. This is the neutrons here, one of them, and they are moving in one direction. There is no neutrons crossing the imaginary boundary for the imaginary cylinder. So let's imagine that they are moving in this direction, and each one of them carry a momentum and has a velocity v. So neutron velocity is v. Speed is the magnitude of this velocity, and the velocity is centimeter per second. And let's assume that the neutron density is n. So n is the neutron density. What do we mean by neutron density? Is how many neutrons, number of neutrons per centimeter cube per second. So this is the neutron density. Let's assume that I have handful of neutrons per centimeter cube per second here in this imaginary cylinder. So what is the volume? The volume of the cylinder, V capital. It will be this distance x multiplied by this area A. So it will be distance x multiplied by area A. And what is the distance x? So this distance x is just nothing but the neutron velocity multiplied by time. Yes? So velocity multiplied by time will give you the distance, multiplied by the area will give you the volume. So in this case, the volume will be nothing more than x multiplied by A, and x is Vt multiplied by A. Now, how we will get the intensity? The intensity is nothing more than total number of neutrons passing by the unit area per second. So this is the definition of intensity. If you want intensity, intensity means number of neutrons per centimeter square per second. Okay, so let's see how we will calculate this one. So we have here how many neutrons inside this volume. So we'll say total number of neutrons in the volume V. Total number of neutrons here is the volume multiplied by the number density, number per unit volume. Yes? So if we have a volume of what? This is the volume V multiplied by N. And this is nothing more than volume V is Vt multiplied by A multiplied by N. Yes? So this is the total number of neutrons inside this volume. Because, yes, go ahead.
Neutron density, are you sure it's per second? Because your units are conflicting.
Sorry, I'm sorry. You're right. So it's a number per centimeter cube. I'm sorry. Thank you for the correction. So now, you multiply the number per centimeter cube multiplied by how many centimeter cube, you obtain the total number. But those total numbers are going where? Are going to the right-hand side. So they must cross the area A. Yes, because we do not, from the first assumption, we do not allow neutrons to cross the boundary. So they do not have any exit except the area A. So if you divide this number, we will call this N capital. So if we divide this N capital by the area, we will get the total number of neutron passing by unit area, passing per unit area. Yes? And if we divide by the time it takes them to cross, so in this case, we will be getting the total number per unit area per second. So in this case, the intensity will be total number is just V N T A divided by T A, and in this case, the intensity will be always NV. So just remember this. If you will continue in nuclear engineering, you have to know that the intensity is NV. Okay? So this is for a monoenergetic beam intensity, NV. Also, the definition for flux, which will come later. Flux, what's the definition of flux? Did you get the definition of flux in NE 495 last semester? So usually flux is number of neutrons per centimeter square per second. But what's the difference between intensity and flux? Intensity are neutrons going with the same monoenergetic energy, same direction. Flux, that they will cross, of course, unit area equal to 1 in 1 second. But the flux, I have the same unit area, so A is equal to 1, and I have T equal to 1 second. But the neutrons are going in any direction. Okay, so the flux is different from the intensity. Intensity going one direction, flux going any direction. And this is a scalar quantity. You will know later on that the flux also can be represented as a summation of NV. If you have, let's say, a flux, monoenergetic flux, that the neutrons, all the neutrons are moving in different directions, but with energy, same energy, it will be NV. Otherwise, if you have different energies, the flux will be the integration over energy of N V of E dE, something like this. I do not want to bother you right now, but I'm just giving you refreshment. So let's move on and explain what do we mean by cross-section. So if we have a target, and our target, we make it thin enough so that the nuclei inside the target will always see the same intensity, neutron intensity. This is why we want to make the target thin enough. Because if it is thick, what happens is the outermost layers of nucleus or nuclei will shield the innermost nuclei. And then the innermost will not see the same number of neutrons like the outermost. So we want to make our target thin enough. And you do not want to, of course, to make it very thin like one monolayer, and then the probability that you have interaction will be very, very small. So the thickness will be X, and the area, total area, will be A, and the number of nuclei per centimeter cube is N capital. And if we have now a neutron beam coming to hit the target with intensity I, the beam, after passing through the target, will be I of X. What does mean I of X? It will be different from the beam in front of the target. Why? Because there is some interaction. So the beam will be reduced by DI because of the interaction inside the target. So this DI is just the number of interacted neutrons inside the target. Number of interacted neutrons inside the target. How we will correlate those interacted neutrons inside the target with the target property and also with the target, with the neutron beam. So we will notice that the total number of interacted neutrons inside the target will be proportional to total number of nuclei per centimeter cube inside the target. So the higher the number of nuclei inside the target, the more you lose from the beam, and the lower, the more you conserve inside the beam. So it should go like direct proportionality with N. And it will also go with direct proportionality with A and delta X. So if you have more area, you have more nuclei. And in this case, the total number of interacted neutrons will increase. If you have more depth, you have more nuclei, the total number of neutrons will also interacted will also decrease. And then finally, It also have a direct proportionality with the initial number I naught here. We call it I naught, I initial. Why? The larger the number of neutrons hitting the target, the more interaction you will have. The lower the number of neutrons hitting the target, the lower number of interaction you have. So this is very normal. So we can remove the direct proportionality, remove this one and put negative sigma or sigma, negative sigma n a dx I naught. And sigma here, what we call the cross section. So sigma is what we call cross section. Why it's called cross section? Because if you look at the units of sigma, you will notice that the units are in centimeter square. So this is number per centimeter square per second, and this is number per centimeter square per second, and this multiplied by this is a volume. So this is what? Centimeter square. This is centimeter cube, and this is what? Number per centimeter cube. There is a missing part here. So this number should be the total. This number should not be di. This should be total. So df, which is di multiplied by the volume, multiplied by the total volume, which in this case a multiplied by delta x. So this is a delta x, because this is the total number of interacted neutrons inside the target itself. So the delta a dx will go away with a dx, and you will end up with, this is number per centimeter square, and this is number only. There is no centimeter square. So let me, what is the B di equals to negative sigma n multiplied by I multiplied by x. So this is multiplied by a, and this is multiplied by a, because this is neutrons per centimeter square per second multiplied by area, which is centimeter square. So this is the total number of interacted neutrons per second. So a will go with a, and you will end up with sigma multiplied by number. This is 1 over centimeter cube. This is 1 over centimeter square per second, and this is centimeter here. So when you remove the area from here and you remove area from here, you will end up with number per centimeter square per second. Will go with number with centimeter square per second, and centimeter will go centimeter cube, and this will give you 1 over centimeter square. So sigma will be, the units of sigma will be centimeter square. Did you understand, or I make it a little bit fuzzy? Okay, when I did the mistake the first time, let me go back again and show you what mistake I did. When I did the mistake the first time, I told you that the di is the number that will be interacted inside here. Yes? But this number is the number per unit area, because the intensity is number per unit area. But I have the whole area A, so I want to calculate how many neutrons interacted in the whole area A. So this is what? A multiplied by DI. So A multiplied by DI, this is the total number of neutrons interacted in the whole area per centimeter per second. Yes? Total number of neutrons interacted in the whole area per second. And this is just proportional to the total number of neutrons inside the nucleus, inside the target, multiplied by the volume of the target, which is delta X, multiplied by the area. And it's proportional also to the initial intensity, or the intensity, and this is negative sigma. So A will go with A, and you will end up DI equal to negative sigma N I dx. And again, if you make the units, you'll notice that this is number per centimeter square per second, and this is sigma. This is number of nuclei per centimeter cube. This is number of neutrons per centimeter square per second, and this is centimeter. So this number will go with this number, and the centimeter will go with centimeter cube, and then you will notice that 1 equal to sigma over centimeter square. Did you understand? Okay, so now this is just, if you want to know, now we knew that sigma has a unit of centimeter square. This is why we call it cross section. But physically, when the neutron will interact with the nucleus, what will happen is, for the billiard ball collision, you will notice that the neutron coming to the target, and this is the target nucleus. So the neutron will see a two-dimensional object like a cross section. So technically speaking, if the neutron passes anywhere near, if this is the nucleus, and we plot around this nucleus some imaginary cross section with radius, let's say, r capital. If the neutron passes here, it will interact. If the neutron passes here, it will interact. If the neutron passes here, it will interact. If the neutron passes outside this imaginary area, it will not interact. And this is why we call the nuclear cross section. It's not exactly the physical cross section of the nucleus, but it is a measure of the interaction with the nucleus. So this is why we call it the cross section. Okay, now what the cross section represent? So this is DI, number of neutrons interacting inside the target per centimeter square per second. If I divide it by I, what does it mean? You have, let's say, 1 million neutrons hitting the target, 100,000 interacted inside the target per centimeter square. What does it mean? So I have 10% interaction. So it is the probability of interaction with the one nucleus, yes? Or with the target, with the whole target. Yes? This is the interaction with the whole target in this case. Yes? So if I divide delta I by I, and then I divide by 1 over n. So what does it mean here? This is the probability of interaction. And when you divide n, what's n? Number of nuclei per unit volume. So this is the probability per unit nuclei, yes? Probability per nuclei per unit volume, yes? And then when you divide by delta X, so this will give you sigma. So sigma is probability. So this is per unit volume. So 1 per centimeter cube. And this is delta X is what? Centimeter. And this is the ratio of those two is unitless. Yes, because I and I, delta I and I, unitless. Yes? So this will go with this, and you will have centimeter square. So it's a measure. So sigma is a measure of probability of interaction. So it's not exactly the probability, but it is a measure of the probability of the interaction with the nuclei of the target. Did you understand? Okay. There is one more definition, which is when we multiply sigma by n. So sigma, what's the units of sigma we just stated? Centimeter square. What's the units of n, capital? So atoms per or nuclei per centimeter cube. But the cross section is what? Centimeter square. So what's the units? 1 per centimeter. So this is called macroscopic cross section. And this is probability per unit base length. Probability per unit base length. So sigma small is called microscopic cross section. So sigma small is called microscopic cross section. Sometimes they call the cross section XS, cross section XS. So so this is the relation between macroscopic and microscopic. So microscopic cross section, macroscopic cross section. Did you understand the difference between both? So one is just bare nuclei, and the other one is the probability, but it's not bare nucleus like here, but this is multiplied by the total number of nuclei per centimeter cube. So when you talk as a nuclear engineer with your friend in a nuclear reactor, usually when you will talk about what's sigma. And sigma, we said that the units is centimeter square. So instead of telling you that the unit is 10 to the power of minus 23 or 10 to the power of minus 19 or 10 to the power of minus blah, blah, blah. So they invented a unit for nuclear cross-section, and this unit is called barn. And the barn is nothing more than 10 to the power of minus 24 centimeters square. So when you talk about how many barn, you knew now that barn is what? 10 to the power of minus 24. So when we say that one of the huge absorption cross-section in nuclear reactor, for example, is xenon. It has a couple of 100,000 barn. And this is why when you run the nuclear reactor for so long time, you produce xenon as a fission product. And if you shut down, it will prevent you from restarting again instantaneously. So you have to wait for a certain amount of time so that you will decay the xenon, and then you will be able to start up again. And this is called xenon poisoning. So when we say, oh, it has this amount, so something like cadmium has a very high absorption cross-section, thousands. Boron, thousands. There is, as we will see in a minute, a cross-section for fission. So many barn. So when you say, okay, I have so many barn, you knew that the barn is 10 to the power of minus 24. And there is sub-barn, something like millibarn, microbarn. And there is kilobarn and megabarn and so on. But usually we will say millibarn or barn or thousands of barn and so on. Again, if you think a little bit, the nucleus will have a cross-section of the atom will have a cross-section of something like angstrom. So angstrom is what? 10 to the power of minus 10. Yes? And the nucleus will be something like 10 to the power of the radius for the nuclear radii will be something like maybe 10 to the power of 14, 10 to the power of 15, or so on. So if you just multiply by r square, which is the area of the nucleus, you will obtain roughly 10 to the power of minus 26, 10 to the power of minus. So this is why they are close. They are very close. Although, as I told you, the physical cross-section has nothing to do with the probability of interaction. The main reason we stated like this is called cross-section is because of the concept that it represents a cross-sectional area. It's not exactly the cross-sectional area of the nucleus. So it's bigger than the cross-section, physical cross-section. Physical cross-section will be 10 to the power of minus 28, 29, or something like this. It's way bigger than the physical cross-section. So this is the cross-section, and those are the units of the cross-section. One of the things also I want to remind you before I go to the definition of the cross-sections here, if you take this equation, di, and you name it of x, because if you remember, this is the target here, and if you look at this target, it has a thickness of delta x, and it has an area of A, and you have the initial beam here, it was I naught, and then once you get out, the intensity was I after a distance x. So let's assume that here is the 0 x-axis. Up to here, I have x, then you interacted within delta x. So from here to here, x, and you interacted inside delta x. The intensity will be I of x here, and here I of x plus delta x. So I of x and I of x plus delta x. So you will see that di of x is just equal to, from this equation, is just equal to di of x equal to negative sigma multiplied by n multiplied by dx multiplied by I of x. If we want to solve this equation, so this will be di of x divided by I of x equal to negative sigma multiplied by n is sigma capital and multiplied by delta x. This is a differential equation, very easy to solve. So you will put the boundary condition. You will say that at x equal to 0, the intensity will be I naught. So the intensity will be I at 0. And at x equal to x, any x here, the intensity will be I of x. So what's the integration of di over I? Len I, yeah? So this will be len I of x from I naught to I of x equal to negative. If this is a function of position, we cannot get it outside the integration. But let's assume that for right now, the cross-section does not vary with distance. Let's say that we have the same material, so the cross-section will not vary with the thickness of the material. So in this case, I can get this one outside, and it will be dx. What's the differentiation of dx from 0 to x? Is what? Is x. So how you will invert this equation? You will just substitute with the upper and lower limits, then invert it. So when you substitute, this will give you len I of x divided by what? I naught equal to negative sigma x, and then you will invert it by, you will say that this is equal to exponential of this, and then you will multiply I of x will be equal to I naught e to the power of minus sigma x. And this is one of the basic nuclear engineering equations. What does it mean? What does it mean?
The thicker your shield is, the more you attenuate the beam.
Yes, it means that the thicker the target, the more you attenuate the beam, because I of x is the intensity after the beam passes through delta x. Yes? So the thicker the shield, the more attenuation you have. And also, what does it mean? If the cross section is very high and you keep the same thickness, so you replace water by boron, what will happen? You will absorb the majority, and then after the boron you will not find enough neutrons, and this is one of the things. So did you understand this? So if you try to plot this in a linear scale, and this is x and this is I of x, you will have something like this. If you try to plot it in a semi-log scale, you will have something like this with a negative slope equal to negative sigma. Did you understand? Now let's play a little bit around, because you will have this manipulation. It will help you a lot in nuclear engineering. So now, what is the probability that if I am here, a neutron will go all the way without any interaction for a distance x, then it will interact within a distance delta x. So it is the probability that the neutron will survive from here up to here, multiplied by the probability that the neutron will interact here. What's the probability of survival? Probability of survival, probability of x, probability of survival up to x. Probability of survival up to x. You will survive, you just get emitted from the beam here, and then you survive up to here, where I can get this probability. This is, let's assume that this is a shield. Yes? What's I of x? I of x is the total number of neutrons crossing the shield without any interaction. Yes? So if I divide I of x by the initial number I naught, this will give me what? It will give me the probability that the neutrons will get through the shield without any interaction. So it is the probability of survival. Yes? So probability of survival is just what? I of x divided by what? I naught, and this is what here? E to the power of minus sigma x. Did you understand this? If you have any question, let me know. Okay, let's move on to the next step, which gets the total number or the probability of interaction now. Let's assume that this is called B interaction, P interaction, and this is P survival. So what's the probability that you will interact in delta x? I just discussed it a couple of minutes ago. You remember a couple of minutes ago when I show you the target, and I said that you have here I, and the number that will interact in is delta I. So I told you that this is Ti of x divided by I of x, and this is equal to what? Sigma multiplied by delta x. Yes? I just showed it to you a couple of minutes ago. And I told you if you divide, sigma is nothing more than sigma multiplied by n. And I told you divide this by n, then by delta x, and this will give you definition of sigma. Yes? So now, I will not divide by n and dx, and I will multiply sigma n, and I make it sigma capital. So this is the probability of what? Interaction within delta x. Yes? So this is probability of interaction within delta x will be equal to negative sigma multiplied by delta x. Okay? So what is the probability that the neutron will survive up to x and interact in the next delta x? What's this probability? It's the multiplication of both probability. It's multiplication of probability that you will survive up to here multiplied by the probability that you will interact here. Yes? So it is B survival multiplied by P interaction. And this will be equal to what? Negative sigma multiplied by dx e to the power of minus sigma x. Somebody will say, what I will do is this. You will not find this in the book, by the way. What I will do is this. Why I will need this. It's very nice to know that later on in the book, if we want to calculate the mean free path, mean free path, they call it lambda, mean free path. What's mean free path? If you are here, the neutron will encounter a nucleus here, knock it, then elastically, then knock another one here, 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 then get absorbed here. So this is the mean free path, let's say. The average of all those interactions, say passes or something like this. I will end up just after I finish this. In order to calculate this lambda, which is the average distance, x1, x2, x3, x4, x5. So the average. How you calculate the average? In statistics, usually you calculate the average by averaging over a probability distribution function. Yes? So if you have a probability distribution function, you multiply it by the quantity that you want to average, then you integrate from 0 to infinity or from whatever you want. Okay? This will give you the average. What is the probability distribution function in our case? It's this one. So when you do this and you integrate from 0 to infinity for x, and p is nothing more than sigma, and there is a negative sign, multiplied by e to the power of minus sigma x dx. When you evaluate this integral, you will get lambda equal to 1 over sigma, which is the total cross section. So in this case, we reach it to the end of the class today, and we understand that the mean free path is equal to what? 1 over what? Sigma. And it makes sense. Why? If you have a very high cross section, like boron, so the mean distance between collision will be very, very small, because the neutron will get absorbed so quickly. But if you have something like heavy water, which does not have high absorption like light water, the neutron will go very far away until it gets absorbed. And this is why in nuclear reactor, in heavy water reactors, you have the calandria for the volume of the reactor is very huge compared to the light water reactors. Did you understand? Thank you so much, and we'll meet next time.